Okay, so in this example, we're going to be looking at uniform motion, which is objects that are moving with a constant speed. And in this case, we have possibly something which is difficult for you to visualize, but basically you go and you have a run with your dog, and at the point you're furthest away from the house, you turn around and the dog runs back to the house. And when the dog gets to the house, he instantly turns around and comes back to you, and so he's bouncing back and forth between the house and you. All the while, the distance between you and the house is getting shorter and shorter. So the question is just asking you, how far does the dog run? So in answering this question, we first draw a picture of what's going on. So here would be you, the runner, and the distance is 3,000 meters between you and home. Over here is home. And the dog is here. Let's see, you're running with a speed of 2.75 meters per second. The dog is running at 4.2 meters per second. And the dog is running back and forth something like this. So he runs in this direction, then he turns around and he runs back, then he turns around, and again and again and again that distance is getting shorter until finally you and the dog arrive at the house at the same time. Alright, now in solving this problem, we do it just like any other. We first drew the picture, then for each object we're going to write down our information. So we have the runner, and then we have the dog. And for the runner, the displacement is known, and that's going to be 3,000 meters. We know the velocity of the runner is going to be 2.75 meters per second, and the time that it takes to get back is unknown. The dog runs some unknown distance, but that's what we're looking for. The speed of the dog is going to be 4.2 meters per second, and the time that the dog takes to complete this task is an unknown quantity, but it's also equal to the time required for you to reach the house. And this is one of those things that you have to look for when you have two objects interacting in the same problem. Not only here with constant motion, but these relationships will exist in uniformly accelerated motion and even in other perspectives that we learn in physics. So we're always keeping our eye out for these types of relationships. In this case, the time for the dog is going to be equal to the time of the runner. Now that we have our information identified, we're going to write out the equations. So we have d is equal to vt for the runner and d equals vt for the dog. There's only one equation you can use with uniform motion or constant speed, and so that's what we have to work with. So we have d of the runner. Let me just put my subscripts on here. Okay, now when solving a problem, you always want to start with the equation that is going to give you what you're looking for. In this case, we're looking for the displacement, or I'm sorry, the distance of the dog. And that means I'm going to start with this equation over here, and everything I do from here on out is meant to embellish and fill in this equation. I don't ever want to do work separate from this equation, and so I'm going to be drawing a series of arrows where necessary to indicate that this is work that I'm doing on the side, and that it ultimately gets substituted back into the equation that gets me what I want. You want to avoid rambling calculations. It happens a lot, and you want to try to avoid that. So we're looking for the distance of the dog, so we'll just write d of the dog is equal to v of the dog, which is a known quantity, and then time. The time is an unknown quantity, so we can go through this like a checklist. This is what we're looking for. We know this, but this is not. So what do we do to get time? In order to get your missing variables, you either have to find a relationship or you have to go to another equation. Alright, so we're going to do our work off to the side. In this case, because there's only one equation that you can work with uniform motion, we're going to have to use the equation that describes the runner. And so I'll write that here. D of the runner is equal to V of the runner times T. Now our goal is to eliminate T from our equation. And we have a T here, and it's this relationship here that allows us to use T of the runner. Now, if the runner and the dog happen to have different times, but we knew what the difference was, for example, maybe the dog was 1 second faster, so then we could say that the T of the dog is equal to T of the runner minus 1 second. Anyways, these happen to be the same, and so we'll solve this equation for T, and we get T is equal to D of the runner divided by V of the runner. So now we'll make that substitution back into this equation, and we get V of the dog times D of the runner over V of the runner. So D of the dog is equal to 4.2 times the quantity 3,000 divided by 2.75. So let's compute our answer, and we get 4.2 times 3,000 divided by 2.75, and that's going to be equal to 4,581 meters, which we can write as 4.6 kilometers if we use 2 sig figs, because technically this is a 2 sig fig problem due to this, and up here due to the 3 kilometers. So this is 2 sig figs. The dog runs 4.6 kilometers while the jogger runs 3 kilometers.